break, and I hope you had the opportunity to watch the refueling process of this hydrogen power bus. So not long ago, nuclear energy and nuclear industry was public enemy number one of the green movement. They denied its peacefulness, they denied its zero carbon emission, they denied its safety and security. Today, without any remorse, they recognize its role in the reduction of CO2 emissions and hail it as savior of the planet. The nuclear industry knows hydrogen by heart, and during the lifespan of a nuclear power plant, which is 60 to 90 years now, it can produce an enormous of cheap electricity by which cheap green hydrogen can be produced. So let's hear about the role of the nuclear industry in the hydrogen value chain. Ladies and gentlemen, two more very short but very important keynote speeches and presentations are ahead of us. Please welcome the NP High CEO, for representing the NP Hydrogen CEO, nuclear powered hydrogen co-production, Sven Nikolai.
Hello. Thank you for being here. I will show you some interesting idea we got. First, from FRAMATOME, working for Covalion. Covalion is a department within FRAMATOME who is taking care of H2 and H2 distribution and refueling stations and battery storage. First I will show you quickly the portfolio, then example of the hydrogen fueling station we recently worked on, and then the NP HYCO nuclear power hydrogen cogeneration project. We offer a wide portfolio of products and services, studies on consulting, engineering, procurement, and construction system integration, and projects and services, customized PEM electrolyzer, log storage applications for H2, and hydrogen refueling stations. Here there is an example of the hydrogen refueling station we recently built in Bielefeld. So in the beginning there was a planning. We built and managed hydrogen refueling stations. This here is for 4 buses per day. The capacity is sufficient for larger 20 buses per day. And at the beginning, we started with 1,000 kilogram hydrogen stationary. Here there is a picture of the during commissioning from the top. So we did the execution of construction work on site, planning, hydrogen of infrastructure, and commissioning. Construction work started April 2021. And the picture was taken 2 months ago during commissioning in April 2022. The first refueling of buses was end of 2022. So there is an overview of this location. We have the plant control, we have the hydrogen supply via trailer on the left side. We have 2 storage areas, one 500 kilogram at 50 bar and 500 kilogram at 500 bar. Hydrogen compressor for up to 500 bar. The cooling unit, of course, and then the bus refueling disperser with 350 bar 2 times. And then we have the space for extension for the larger 20 buses. So here is the main focus. Why I'm here is the idea of this nuclear powered hydrogen cogeneration. It's founded by the European Commission. We have 10 consortium partners. One is, for example, Untitled, but also the CVR is from Czech Republic is a part of this consortium. So why this idea came? So The H2 plant needs electricity, needs cooling water, needs deionite water, so needs nitrogen supply and all that stuff. And so all that is available in the auxiliary of the nuclear power plant. And especially in the VVR 440, we were told, or we know that this load follow operation, when there is a big amount or of green energy like PV or wind or something available, then we have to be in the load follow operation. This is very difficult for the nuclear power plants, especially for the VVR 440 type. And this is why this concept or this study focus on this 440 type, but it is open for all the other types. There is technical aspects, there is economical aspects and operational aspects to be considered, which are already available in the nuclear power plant, and therefore OPEX and CAPEX costs could be reduced for the H2 plant. So large electrolyzers, as you heard this during the day, and you are aware, the hydrogen demand in Europe is expected to be increased very much. Though this is, I think, almost half a year old, this slide, so probably it's in the meantime larger. So it's expected with 40 gigawatts at 2030. As I said before, so light water reactors operate often in part or load-dependent mode. Their energy production capabilities remain partly unused. The profitability decreases, and so our proposal is this use of the surplus nuclear electrical power for the production of hydrogen. What was said before is that 1 week ago it was issued that a new directive says that you need to have 100% dedicated energy source to have the green label for green hydrogen. This is not considered in my slides, and I think this directive, if this is correct, need to be discussed, I think, because there's some problems. So the hydrogen can cover the hydrogen demand of the plant. Hydrogen is used for cooling in the nuclear power plant. It can be used and sold for fuel mobility or industrial applications, or serve as tradable electricity disposal for other grid operations we heard before. Advantages by a coupled operation of nuclear power plant and H2 plant is reducing of consequences of load follow operation demands, allowing load follow operation without reducing reactor power, reduces wear and tear on a nuclear power plant's components. The side advantages of the nuclear power plant is cheap and abundant electricity available. Additional transformer might not be necessary. The deionized water is available. Additional purification for electrolyzers might not be necessary. And the cooling water circuit is also available on nuclear power side. Economic advantage is the reduced of CAPEX OPEX due to existing power, water, gas supplies, and the diversification of the nuclear power plant product portfolio via the H2 business. Once again, as said also in the other speeches, H2 can be used for grid stabilization via fuel cell or gas H2 turbine, hydrogen mobility, buses, cars, trains, industry, add H2 to the natural gas supply system, chemical feedstock. So business case top level, you have the nuclear power plant. You sell it either to the grid or you buy it to the H2 plant. And the H2 plant sells the hydrogen then to either to the nuclear power plant or transportation industry or the. So the benefit is self-produced H2 to cover the H2 demand of the nuclear power plant, reduce the fire load due to no H2 storage on nuclear power plant site, continuous operation optimum load curve, which increase the profitability and reduce the cost for maintenance due to reduced load changes in the material, additional income selling H2 to customers, easy switching into increased H2 production when prices for electricity are dropping during a day. Load follow operation just by switching from grid to H2 plant without reducing the reactor power. The benefit for the H2 plant is the use of auxiliary systems already available at the nuclear power plant sites, like deionized water, cooling water, electrical power, nitrogen supply, pressurized air, etc. The known safety culture from the nuclear power plant personnel, synergies for the service personnel with the nuclear power plant can even be operated from the control room of the nuclear power plant. So, project development. So, we start with the decision to initiate the project, feasibility study, investigation of technical, economical, and licensing, perform forced analysis, finding stakeholders, drivers, barriers, showstoppers. When this is successful, we continue with the decision to start concept phase, establishing firm definition of the design, select the preferred commercial and technical concept, set targets for the cost schedule, plans, feed, and execution. So then we enter the final investment decision. We perform the basic design and submit the permission documents, perform the detailed design, and select sub-suppliers. Then building permission is the phase 4 and the execution. Then perform the manufacturing of the components of the building, erection and civils, delivery of components, cold commissioning. And at the end, operating license, plant rent up, implementation of H2 production, hot commissioning, test transplant, production ramp up. This is an example of a Siemens large electrolyzer. So we are also cooperating with Siemens. So in the front you see one module, and by building this in a row, you can increase up to 100, 200 megawatts electrolyzer. This is also from the, let's say, better times. This, this landscape. In red, you see the VVR 440 plants. Green are the VVR 1000, blue the VVR 1200, and yellow the VVR 1300. Okay, Russia is not anymore an opportunity, but as I said there. Besides that, there is discussion to extend this, or when it's once worked, and we have a pilot site defined to bring this also to other kind of light water reactors like France, like Netherlands, Spain, or the US. Thank you very much.
Thank you, Sven, for this presentation. And then I kindly ask to join me on the stage representing the Center for Energy Research, to talk about the utilization of nuclear power plants for hydrogen production. Mr. Attila Imre.
Thank you very much, and thanks for the opportunity to have this lecture here. The previous presentation was a very nice presentation about a well-defined project. Now I will talk about a more general approach. Generally about the utilization of nuclear power plants for hydrogen production. So there are several methods to produce hydrogen. Some of them are well developed. Some of them is just promising, and there are several which is only in lab scale. The already existing and mature methods are the electrolyzers, alkaline electrolyzers of water, the membrane electrolyzers. Oh, beautiful! The membrane electrolyzers of the also the water, and the so-called steam reformation of methane. This steam reformation is a high-pressure reaction between methane and water, which makes a lot of hydrogen, but it's a gray hydrogen, so we do not like it. The promising technologies, there are also another electrolysis technique. It's called solid oxide electrolysis. It's a very high pressure, very high temperature technology. The so-called dry reformation, when the methane is broken to carbon and hydrogen without adding water. The direct thermolysis water, when the temperature is so high that you can break the bond between oxygen and hydrogen, and from water you can directly produce these two materials. The so-called thermochemical decomposition, when you are using some additional materials, so the breaking of water is not a one-step process, but a several-step one, using some catalyzer or some intermediate chemical compound. The thermochemical decomposition of some other organic materials, usually these materials are fossil materials, so we also do not like this method. The so-called partial oxidation of methane, this is a well-known old method when they are producing the mixture of carbon monoxide and hydrogen. The so-called coal gasification, it's also a high temperature reaction with hot coal and water. And the biomass gasification, when the biomass is heated up and some of the product will be hydrogen. And there are lab scale methods. For example, there are some algae which can produce hydrogen. The efficiency is not very high. There's the radiolytic decomposition of water when they are using some radiation to break the hydrogen and oxygen bond. And there's some special kind of electrolysis when they are using some microbes to help the processes, and also the so-called artificial photosynthesis. So the actually the first column is what is mature enough to be used, and the middle column can be used in maybe 2 or 3 years. As you can see, in some case, you are starting the process from water, which is something green material, or from biomass, which is also considered as a green material. In other cases, you are using, for example, methane, which is from natural gas. We are not concerning hydrogen production from natural gas because it's not carbon-free method. Actually, there is one method which is not good, coal gasification. It is using water, but it's also using coal. So there are some carbon monoxide and dioxide involved. So we have to remove this one from our list. What is the good hydrogen? What we would like to produce? We would like to produce hydrogen from water or from some renewable organic materials. And also we would like to do it with zero or nearly zero carbon emission during this production process. What can be provided by nuclear reactors to produce hydrogen? Actually, there are 3 products of a nuclear reactor or in general for a nuclear power plant, which can be used in our purpose. As the previous lecturer said, we can use the electricity. So if you have electricity produced by this nuclear power plant, you can do electrolyzers and you can produce hydrogen. You can also use heat, and additionally, you also have radiation. So with radiation, you can also produce some hydrogen, but we are not considering this here. Only electricity and heat will be considered. First, I would like to start with heat. Theoretically, the best method to crack water is to heat it up to 2000, 3000 centigrade, when it will be all the bonds will be broken and hydrogen and oxygen will be produced. It happens in very high temperature. I mean, if you want to break all molecules, you have to reach at least 2000 centigrade. If you would like to break only some molecules, for example, 20%, which is also quite a big number, it's enough if you are reaching some temperature around 100 centigrade. 1000 centigrade. 1000 centigrade is also pretty high temperature. If we are using a traditional nuclear power plant, for example, the ones which was shown before, when the water used as moderator, you do not want to reach high temperature when the moderator will turn to hydrogen and oxygen, because it wouldn't be very healthy for the reactor. So this method cannot be used in generation 2 and generation 3 nuclear power plant, which are using water for moderator and cooling material. There are some new reactor techniques, the so-called generation 4 reactors. They're using molten salt, molten metal, or helium for cooling and also for moderation. And in those reactors, theoretically, this temperature can be used. So you can reach 1000 centigrade. But the problem that if you want to produce hydrogen with this 1000 centigrade, first you have to take away this temperature for a safe distance, because no one would like to have hydrogen in the middle of a nuclear reactor. I think it's not necessary to say why, because it's a very explosive material. And if you want to transfer high temperature material, the heat loss will be quite high, and also you need an extensive amount of heat transfer material, which have to be some very special material, because 1000 centigrade has to be reached. The second opportunity, this thermochemical reaction, when you are using some material to help this hydrogen oxygen break, and it can happen in lower temperature, around 600, 900 centigrade. The 600, 900 centigrade might work for generation 4 reactors. So I would say that if in 10 or 20 years people will build this generation 4 reactor, it might be possible to build cogeneration reactors or cogeneration plants, when part of the capacity will be used for heat production and hydrogen production, and part of the capacity will be used for electricity production, and the electricity will go to the grid. And this technology, well, it needs some further research, but might work in 5 or 10 years. The last method concerning heat, as I mentioned, there are some biological or biochemical reaction which can produce hydrogen as a side product. The efficiency is very low, so it's not for mass production, at least not in this moment. There are very extensive research in this field. So in a few decades, or maybe just in a few years, there might be some breakthrough. The good news that these reactions needs only 50, 60, 70 centigrade, which means that even present reactors can provide this temperature. And when we are talking about 40 centigrade, for 40 centigrade, even the so-called tertiary waste heat, which is, for example, we know, most of us know the Pax nuclear power plant. The 40 centigrade water is the bad water that is going to the river Danube and making it too hot for summertime. So this would be a much better use for that water. For the productions using heat, there is one general problem. When you are cracking water, then the hydrogen and oxygen will be produced in the same place. Mixture of hydrogen and oxygen is an explosive material, so you cannot do it too close to the reactor, therefore you need to do it in a safe distance. The second way is to use the electricity. The electricity by nuclear power plants is definitely carbon-free electricity. Well, we can talk about whether it's green or not, but I would say that presently it's considered green, but it's not a renewable electricity. What is very good for us that the nuclear power plants are so-called baseload plants, which means that they are providing nearly constant power, and because we have constant power, not the very fluctuating power provided by a photovoltaic plant, therefore hydrogen production would be predictable, and people of the industry like predictable methods, not very scattered ones. As I mentioned, there are at least 3 different types of electrolyzers. Which is considered best presently is the membrane or PAM electrolyzers. These electrolyzers can handle fluctuating power, so they can be used with photovoltaic power plants, but they are quite expensive. The so-called alkaline electrolyzers, which are non-expensive, or the solid oxide electrolyzers, which are also expensive but very efficient, they need constant power, and this constant power cannot be provided by wind or solar sources. So therefore, it might be good solution to use nuclear power plants for this purpose. So actually, there are 2 opportunities. First, that we can build a huge photovoltaic power plant when we have a lot of surplus energy, but we are not using the surplus energy. We are using the basic part of the produced energy to produce electricity, to produce hydrogen, because in that case we can use, for example, solid oxide electrolyzers, which can work on very high efficiency, or we can build nuclear power plants or use the nuclear power plants for the same purpose. Of course, very green people would like to say that let's build photovoltaic power plants, but also we should consider that, for example, hydrogen should be transported away from this production facility, and usually nuclear power plants has very good infrastructure. There are roads, so it might be much better to produce close to these facilities. I would like to say that the best solution would be a combined effort. You can see the green part. The green part is a photovoltaic off-grid high-capacity photovoltaic power plants. Okay, you can see that the power is changing pretty much. It means that you cannot use it for alkaline or high temperature electrolyzers because it needs constant power. But I would say that, okay, let's take a nuclear power plants and let's have a balancing power taken away from this nuclear power plants. That's the blue part. So the green part is from photovoltaic, add some blue one from nuclear power plants, and in this way we can provide a constant power which can be used to produce hydrogen by electrolysis day and night. And the good thing is that practically this could be done in a few months, because we have nuclear reactors, we have photovoltaic power plants, even sometimes we have them together. So all what we need is electrolyzers. Electrolyzers are very expensive now, but that's mostly for the membrane electrolyzer. So if you would like to buy alkaline electrolyzers, you can do it for much less expenses, and for you can buy even a few 100 megawatt if you need it. And well, can you believe that this is a nuclear power plant? It doesn't look like a nuclear power plant, but this is a nuclear power plant. This is the Temelin one. So there are several nuclear power plants which already has the photovoltaic part. So to build a hydrogen producing facility here, when you are using the photovoltaic electricity balanced with this nuclear power plant, I think this might be a good solution which can be utilized even in a few months. So, of course, it needs some money, but everything needs money. And thank you for the opportunity.
Thank you very much. So nuclear power plants can play a very crucial role in this whole hydrogen ecosystem. Thank you very much for this presentation. So I think the key message is that we have to think outside the box in a way, because we are talking about a brand new thing and we have to find out which is the best way to develop. But at the same time, we have to use our current facilities, like the pipelines, like the nuclear power plants, etc. And we have to put it in a broad context. How can we use the hydrogen in the near future? One thing is very important, very clear. We have to think about it and we have to use it. We do not have too many other choices. So for some closing remarks, I kindly ask to join me on the stage the organizer of this event, the Hungarian Hydrogen Technology Association. Please welcome the president of this association, István Lepsényi. He started the day, and now here is the opportunity to close the event and our conference, let's say a 2 days event here at the ZalaZone. Mr. President.
Thank you very much. Thank you. First of all, I would like to thank you all the participants, because I think that these 2 days was very, very useful and very, very important. Number one, yesterday, this is about the youngsters, about the future, about the technology. And we were very positively surprised with the interest of the students and their agility to look at it. Today we have seen a lot of sometimes comprehensive discussion and presentation, but I am absolutely sure that we learn a lot. And we also agree that such a type of meeting we should repeat, we should share the different experience, the different best practices and the knowledge. And by that, we can really improve the speed, what we have to do to reach our targets for a better world. So thank you very much, and thank you all of you.
Thank you very much for the whole association and the whole team for organizing this event, and thank you very much for attending. Ladies and gentlemen, have a safe trip back home, and see you next time. Thank you very much for being with us in the last 2 days. Thank you very much. See you soon. See you next time. Bye-bye.